What configurations are needed to become meltdown proof? Can all of them become meltdown proof? And if so, why aren't all meltdown proof? And this is coming back to molten salt reactors. The proponents of thorium like to say it's meltdown proof because they have a salt plug. That just is something you can do for any molten salt reactor. And it doesn't make it meltdown proof. It means that if you do nothing, and the reactivity gets so high that you have basically a runaway reaction and it gets hotter than it should, it'll melt the plug, it'll drain out, and it'll become subcritical, and it will cool out passively. And so in that sense, it's already molten, but the thing that you're preventing is just a phase change. And so it's not a meltdown per se, it's a phase change. You don't want it to go from solid to liquid, like what happened with Chernobyl, and you don't want it to go from a liquid to a gas, which would be basically like an explosion again. You would have a chemical disassembly of the system, like what actually happened with the water in the Chernobyl reactor. It flashed to steam, and then that water flashing to steam, it provides basically a chemical explosion to disassemble the system. And that's what you don't want. You don't want a chemical disassembly of the system from a phase change in the fuel. And the key is that you can either make the fuel so that it can withstand all of the heat from a runaway reaction so that it will turn itself off, and all of the residual heat will not cause a phase change. So there's a lot of different ways to do that. In the past, the perspective was, well, we'll design it safe enough that it's sufficiently unlikely that it makes it acceptable from a regulatory standpoint. And that's what happened at 3 Mile Island, which also is why it had a negligible release. It scared a lot of people, but it had a negligible release. And so at 3 Mile Island, we felt that it would, it was safe enough that you're not going to hurt anybody. And when we got that, we found out that that's not what the public wants. The public actually wants it to be much safer than that. And so that's what we did. And that's what we provide now with probabilistic risk assessment. And so the salt plug, it's kind of the same approach. You're assuming that nothing's going to prevent that. And those are the same kinds of assumptions that you can make in any other safety system design. What I really like about the modern reactor concepts are the ones that are sufficiently passive safe, walk away safe, don't need to do anything. All that they'll do is just get really hot and be really expensive, and you're not going to have a phase change. So it's really just the phase change that you're mitigating through materials, and material science has allowed us to do that. So hope that answers the question. Thanks for asking it. Bye.